All right, thank you. And I'm actually ended up keeping my camera off here. I don't have the best lighting in the room that I'm in, so I'll save everyone from seeing me there. Hey, thanks for the quick introduction, and thanks to everyone joining to talk about a topic that remains very near and dear to my heart, damaging winds produced by gravity wave associated convection, or GWAC for short. And I know I've talked in this call it the series of presentations. I know it's evolved over the years to now the Innovation Spotlight, sort of introducing this topic, what it looks like. And now I figured a new iteration is doing a case study of a recent events that actually took place across the Southern Plains just last month. And it was a really interesting event. It was not well forecasted, which is pretty typical at these events, but it was actually very high impact. So I figured it's a good one to take a look at and see what the forecastability was like. So why don't we jump right in here? A brief overview of the event is during the late evening and overnight hours. This was April 4th to April 5th of 2025. There's a pretty impressive damaging wind event that took place from a gravity wave associated convective cell. It started near the Red River, just near Wichita Falls, Oklahoma, and then stretched all the way toward Tulsa, Oklahoma. And it produced a nearly continuous swath of high-end wind damage, over 100 miles worth of wind damage, with measured wind gusts ranging from 60 to 86 miles an hour. That's from the Oklahoma Mesonet. They have some great sites across the state there for catching severe wind gusts. But based on the wind damage reports, I strongly suspect that the wind gusts are actually closer to 100, even 110 miles an hour in spots. There are reports of homes that were destroyed, farm buildings that were destroyed. There was a trailer truck that was flipped, an RV that was flipped. Even a radio tower was collapsed. So this is some pretty high-end wind damage and really not all that atypical for these types of events. And what was really impressive is that these winds, they occurred out of the southwest with the storm. They took place in spite of opposing northeasterly synoptic winds, and those synoptic winds were gusting as high as like 35 to 40 miles an hour. So effectively, the storm was producing like 100 to 130, 140 mile an hour net wind when you take into account the opposing flow. So I would say that's really on the upper echelon of these kinds of events, but it seemed like a really good one to take a deeper dive into. Just to show a little bit more in depth, and we're obviously going to get much more into the radar data later on, but just a really continuous swath here of wind damage, really along the or crossing the I-35 corridor in southern Oklahoma. So first, I figured we can take a little bit of a dive into the forecast guidance leading up to this event. And before we jump in, I still want to mention that there's a lot we still don't understand about these events. I think there's like cookie crumbs where we can sort of start putting the pieces together. But I do want to put on a big caveat that what I'm going to discuss here does not necessarily reflect like a much better understanding of how to forecast these events. It's just trying to see a signal where there may be a signal, hopefully not just noise. So we're going to be relying a lot on the HREF here leading up to the events. And we're going to be looking at the 12Z HREF and the 0Z HREF, roughly 18 and 6 hours respectively, prior to the convective event unfolding. So from a synoptic point of view on the left-hand side of the slide here, looking at the mean 500 millibar flow, there is a kind of a stagnant upper level trough, positively tilted upper level trough across the southwestern U.S. And there's an embedded shortwave that was actually traversing through northern Mexico into southern Texas. And it's a little bit hard to see because there's some terrain effects and some smearing effects due to the mean field here. But you can see that shortwave propagating into Texas. And that actually is a somewhat favorable pattern for mesoscale wave genesis is when you have a shortwave that's basically propagating through a bigger trough, going from positively tilted to negatively tilted, especially as the wavelength shortens between, let's say, the trough and the ridge axis. I'm not going to claim to be a really good synoptician, but basically when this happens, you get an imbalance of your upper level flow. Your ageostrophic wind component gets really, really large. And when that happens, the atmosphere is said to be unbalanced. And the way it resolves that balance is through basically generating gravity waves. I will say that just looking at a 500 millibar chart is kind of a fast and loose way of looking at this. It's more proper to look at something called like the Lagrangian-Rossby number. That's a mouthful, but that's really comparing your ageostrophic wind component and your geostrophic wind component to really see how much imbalance there is. And I'll just show an example. This is from a completely different case, but what this may look like. The white contoured fields, that's the Lagrangian Rossby number computed for a upper level shortwave that was moving through the Great Lakes. This was a few weeks ago in mid-April, highlighting basically like northern Iowa toward like central Lake Michigan as a region favorable for gravity waves. And this is I think a 2 or 3 day forecast that ended up verifying with a cluster of gravity wave cells that moved into southern Wisconsin, producing baseball size hail and eventually damaging winds in lower Michigan. So this is probably a more thorough way to look at imbalance in the atmosphere, but it's not very intuitive. I mean, how many of us look at the Lagrangian Rossby number every day? I certainly don't. But I just want to say that looking at the 500 millibar height is not exactly the best way to look at this, but still just figured it's something we all look at most of the time. Looking closer to the grounds on the right-hand side, that's just the mean surface map. You can see that there is like strong northerly flow across much of the southern plains behind a cold front, or really a stationary front that was present across south central Texas. So really the trajectory of the shortwave is going to be moving over a stable air mass, which would be favorable for ducting of gravity waves as well. So from sort of like a 5,000 foot level, I guess I should say a 500 millibar foot level, this sort of fit the conceptual pattern favorable for gravity waves. Now, if we look at the amount of at least the low level flow, left-hand side is 700 millibar wind, right-hand side is 850 millibar wind. It's actually pretty interesting that the environment across like Texas and Oklahoma was like extremely sheared. The flow reversed from 700 down to 850 millibars, which is pretty interesting. Admittedly, I'm not like super confident if that's really important with these gravity wave cases, but it's just interesting to show that you had a really strong shearing layer really across Oklahoma there. And just to hit that point home, generated a reanalysis sounding here, really a hodograph, I should say, and the wind direction like literally flipped between like the surface to 2 kilometers, which is pretty interesting to see. So just kind of a novelty for this particular environment. If we look at the instability parameters, left-hand side is going to be the most unstable cape, right-hand side is surface-based cape. Based on the trajectory of the shortwave into central Texas and southern Oklahoma, very clearly far removed from the surface-based instability axis, but even on the fringe of the mu cape axis. So just from a 50,000 foot level, maybe not super favorable for convection in central and Oklahoma because it's just so far removed from the instability. If we look at soundings roughly 6 hours prior to the event taking place at Fort Worth and Norman, you can see there definitely was that gradient in the mu cape. You had steep mid-level lapse rates, well, I guess relatively steep for the central plains, but definitely more mu cape in Texas than there was in central Oklahoma. In fact, quite a bit of dry air in central Oklahoma. So just looking at the sounding by itself, you wouldn't necessarily think it's super favorable for thunderstorms with only about 300 to 350 joules per kilogram of mu cape analyzed. Now, there was what we call a critical layer on the Norman sounding, and the critical layer is defined as where your wave relative wind speed is 0. And I know that's a little bit more of a mouthful there. The thing about critical levels is it's kind of a catch-22. You don't necessarily know if you have one until you know what like the phase speed of a gravity wave will be. So it's kind of hard to look at a sounding and say, oh, there's a critical level, because you don't know if you even have a gravity wave. But the reason why that critical level is important is that sort of acts as a lid on sort of how deep or how tall gravity waves can develop. So just to show this schematically here, kind of a conceptual model of how gravity waves work. You have what's called a ducting layer, and it starts with basically a low-level inversion. That's where the gravity wave originates, and then your critical layer. That's really, again, the top lid of how deep your gravity wave will grow. And since the critical level is typically above your low-level stable layer, it often encompasses a region where there's actually convective instability. And you can see that in this conceptual model here. So if you do get a gravity wave, it can very easily become aligned with convection and even sustained convection. Just to visualize that here as your stable layer oscillates, you can see it's exciting or perhaps even activating your elevated instability. So it's just sort of a conceptual model of how these convective gravity wave events can really kick off. Now, one thing that I really like to look at when forecasting thunderstorms, especially from an aviation perspective, is this field in the HREF. It's basically, it's the 4-hour max, wherever the simulated reflectivity is greater than 40 dBz, wherever your mu cape is greater than 50 joules per kilogram. So it's sort of like a calibrated probability of thunder. That's sort of what we call it here in our office. What I also have overlaid here are going to be the reports and the warnings. The blue warnings are severe thunderstorm warnings, red are tornado warnings. Left-hand side is sort of the greater lead time. Right-hand side is the shorter lead time. But we'll see that the observed severe weather and the warnings were right on the edge of where most cam guidance had really any convection, and which matches where the mu-cape axis was located. So it's pretty interesting to see actually that like in the bullseye, or I guess the streak of where the highest probabilities were for thunder, you almost had a dearth of warnings and no reports for severe weather, which is pretty interesting. The one other thing I'll mention here, and I know I'm kind of jumping around, is this event was actually very well warned by the Norman Forecast Office and the Tulsa Forecast Office. For better or worse, this storm was also producing a lot of severe hail, which gave the offices a good reason to have a warning out. I'm not sure if they expected the damaging winds, but it really worked out in their favor where all of the reports were within severe thunderstorm warnings. And that's not always typical with these cases. So do have to applaud those offices for having this whole swath and warnings. That's definitely a good feat right there. Just a few other HREF parameters I want to look at here. These are going to be the ensemble updraft helicity swaths. So really looking at threats for supercells. Again, left-hand side is the greater lead time, 18 hours of lead time. What's pretty interesting here is most of these reports were not associated with any like simulated supercells. On the right-hand side, I guess there's a couple little swaths there that show up, but again, just signals a lower probability for severe weather just based on the HREF in this forecast scenario. Since we're talking about damaging winds, I figured it's good to look at the ensemble wind swaths as well. And this one was a little more interesting to me, especially with the 0Z HREF just prior to the events. You'll notice that there actually was a pretty good paintball swath that lined up really nicely with where the observed damaging winds were located. Granted, this is a paintball of 30-knot winds, so maybe not necessarily the wind speeds that were observed, but very clearly there was at least one or two members from the HREF that actually resolved the observed storm, which is really interesting considering the real lack of instability. And that speaks to the fact that cam guidance can forecast these events. In my experience, it may not be exactly correct in the location or even the time. This is probably one of the more impressive examples I've seen where a few cam members actually nailed the location. That's definitely not typical. One thing I will caution with using cam guidance, however, is if the wavelength of the gravity waves is not necessarily ideal based on the resolution of the cam guidance may miss it entirely. So let's say if you have gravity waves that are, let's say, higher frequency, a much shorter wavelength. Remember, like, think of like a Nyquist frequency, or if you think about like different sampling of a wave, you need like 3 points or 5 points to get the inflection points, the trough and the ridge. So if the resolution of your model isn't high enough to capture that, the model's not going to get the gravity wave. So evidently something about this environment, whether the synoptic scale or mesoscale environment, was favorable enough where at least some cam guidance was able to capture a gravity wave. Now, those are the paintballs of the winds. This is looking actually at the max wind gusts, just to see if it had an idea about the magnitude of the winds. Again, mainly the lower lead time, the 0Z HREF just before the event did have that little swath of higher winds across southern Oklahoma, but it peaked at about 50 knots. So probably not quite correct with the magnitude, but still it had a signal in the location of hey, just north of the Red River, there could be an issue with damaging winds. Now, taking a slightly deeper dive into the cam guidance, I typically don't like looking at cam guidance at face value because it's only a simulation and one outcome, but just kind of want to compare the observed radar to some of the cam guidance that performed a little better. There were 3 members that did okay. Interestingly enough, the HER from about 24 hours prior to the event actually did pretty well. Just looking at the observed gravity wave associated convection, you can see the HER guidance actually did depict like multiple bands of equally spaced convective cells, including a dominant cell that went into southern Oklahoma, which is pretty impressive for a 24-hour forecast. And even 6 hours prior to the forecast, the HER still did okay, showing a more dominant band across southern Oklahoma. I wouldn't say it was nearly as good. The model that did look like it performed the best was the NSSL WRF that had a real dominant convective band move across southern Oklahoma. So it's just really cool to see cam guidance providing a signal that this may happen. And A best practice that I could recommend is, if we see the favorable synoptic environment, even hints and cam guidance, you still don't want to go all in. It'd be no different than if, let's say, the HER was showing like a huge supercell moving through Oklahoma City. We wouldn't want to write an AFD saying, well, the HER says there's going to be an F5 tornado or EF5 tornado, right? What we would do is we would kind of put it into our mental toolbox of what do we think is going to happen today? Think of our our mental PDF of the different probabilistic scenarios. And in this particular case, there's 3 HRF members that show damaging wind producing GWAC. Does that mean it's the most likely outcome? Probably not, but it's one of those things we have to watch for in this type of environment. So it's one of those kind of messaging paradigms. And actually, I forgot I had a slide on that. How much stock can you put into 3 individual HRF members? Probably not a ton, but it's one of those where it's like, okay, this is something we may have to watch out for. So the workflow that I like to go through is trying to recognize these synoptic patterns supportive of these types of gravity waves, maybe identify a few cams that have the signal. And then from that point forward, you just watch trends in the radar and the observations like a hawk. And once you start to see the event unfold, if you do go down that pathway of damaging winds being produced by gravity wave associated convection, then you pivot your operations, you're in warning mode, and you just warn it until it dies. Is sort of how it goes. I will say throughout the spring, we've had actually quite a few successes of forecasting favorable environments. Maybe have been a little off in location and time, but I'm gaining confidence that we can forecast these events and forecast when there may be severe weather produced by these events. So how did SPC do with this event here? Keeping in mind this is a really challenging forecast with a really low signal. Most of the reports were within, actually all of them were within severe probabilities, and it really straddled the line between the slight and marginal areas, so the level 2 and level 1 severe weather threat areas. And it was right on the edge of the damaging wind probabilities, but generally speaking, the outlook featured generally low probabilities for severe weather. And I grabbed the 1Z outlook. This is like just hours before the event actually unfolded. And the swath of damaging winds was in the 5% wind area. It was outside of any SIG wind area. In fact, I don't think there were any SIG wind probabilities for this particular outlook. And that is actually pretty common with these gravity wave events. We did a quick little study looking at like a 3-year climatology of wind reports produced by these events. And there isn't a single SIG wind report that occurred within SIG wind probabilities. So what that means to me is that if the experts in Norman aren't able to forecast it, then it's really, really difficult. These are really difficult events to forecast. The SIG winds often come as a surprise. But with that said, I think it would have been reckless to have SIG wind probabilities in this kind of scenario. You have 3 HRF members that show a threat for damaging winds. None of them show wind gusts greater than 50 knots. So what support would you have for SIG winds? So this is not a critique on them at all. It's just showing that this is a really difficult forecast. And I consider it a big win that they even had severe weather probabilities in this swath, considering there was like really meager MUCAPE. So my hat is off to SPC for having severe weather probabilities. And again, my head is off to the offices that were impacted for having this entire swath warned. So yeah, probably not worthy of having higher severe weather probabilities based off of the signal and cam guidance. All right, my slide is not advancing, so let's see what's going on here. There we go. All right, so we talked a little bit about the radar analysis, or about the environmental analysis. Why don't we take a slightly deeper dive into what the radar actually looked like here? So there are 3 primary stages to this event. I would say there is an initial development stage, a mature stage, and a dissipation stage. So when the storms first developed across central Texas, there were multiple storms that developed in a general warm advection regime. I actually find that's pretty common in these events for gravity wave convective storms to develop in a broad region of warm air advection. With time, 1 or 2 of the storms became quite dominant. And you can see that band that's developing just on the northeastern side of the radar loop. That is eventually that storm that became dominant. It's not clear to me why that's the one that became dominant, especially since like the segment that went across, well, I was going to say central Texas. I guess that's not very descriptive, but the cell across the central part of the loop was like longer lived, but for some reason it didn't become the most dominant. And the thing I want to say here is even though we talked about the synoptic pattern favorable for gravity waves, it's quite possible that that's kind of a red herring. There's a lot of studies that show that like just updrafts within like elevated storms can actually generate their own gravity waves. So it's possible that as these storms developed, for whatever reason, this lead storm developed a much stronger gravity wave by itself, or maybe in tandem with the synaptic gravity wave. I really don't know. And I think that's something we really need to study a little bit more as the source of the gravity waves here. But the lead cell eventually did become quite dominant and start producing a damaging hail. Now, as the cell approached the Red River, I would still say it's in an initial development stage, but a signature of surface wind production started shortly after 6Z. And what I mean by that is you can see the northeasterly synaptic winds. The radar is in the kind of top left corner here. You can see a weakness in the wind, even some of the green showing up, some inbound return showing up. With the synaptic winds blowing 30 to even 40 miles an hour, that would suggest that this is producing maybe 30 to 40 mile an hour winds at the time, just as it was passing any given location. Maybe it was just like leading to a brief period of relatively calm winds. I looked at a lot of personal weather stations in this general vicinity, especially across Wichita Falls. And there were a few home weather stations that gusted 30, 35 miles an hour. But what was more impressive to me is how early on the storm was associated with an impressive pressure jump. That's a 10 millibar pressure jump very early on in the life cycle of the storm. That's a pretty upper echelon pressure jump. And a lot of the cases I've looked at were more in the neighborhood of 3 to 5 millibars. So the fact that this had a 10 millibar pressure jump so early on was probably foreboding that this was going to be a bigger storm, more of a high impact storm. But generally speaking, it just was producing severe hails that approached the Red River, which I think was very fortuitous because it allowed the forecast office in Norman to have justification to have a severe thunderstorm warning on this storm before it even started producing severe winds. Now, once the storm crossed the Red River, that's when it went on its rampage and started producing just a continuous swath of high-end wind damage. Unfortunately, the radars from Wichita Falls and Norman did not have the best radar angle. In fact, the storm was moving almost like oblique to the radar angles through the entire life cycle. So it really didn't have a great opportunity to see it like a damaging wind signature. But I will say is like, I'll let the loop reset. Just east of Wichita Falls, you did start to see signs of a divergent surface couplet. It was in a region of low reflectivity, so it's hard to say if it was legitimate, right there. And then especially when it was moving closer to the Norman radar, you did see that there was evidence of a surface divergence couplet. But notice that all of the wind reports occurred sort of without the radar signature, and that just speaks to the limitation of using radar sometimes to look for damaging winds. It wouldn't matter if this is a rear and flow jet driven system. If you just don't have a good radar angle, you're not going to see it. So I'll say it one more time. Very impressive that this entire swath was warned by the Norman and Tulsa offices, considering that it was very low predictability and not really optimally aligned with the radar beam. But through this time period, it produced that continuous swath of damaging winds. As I mentioned, I suspect it was greater than 100 miles an hour in certain spots, just based on the character of the wind damage. As the portion of the storm moving toward OKC, it had a really great beam angle to take a cross section. I always like taking cross sections through these storms just to see what it looks like. What's really neat is you can actually see the gravity wave lifting upward and then eventually decaying here. And you could actually start to see some oscillations of the gravity wave as it moves over the radar and eventually north of the radar. So that's a pretty classic signature with these types of events. You see the stable layer being lifted. And this, I'll let the thing reset again. But earlier on in the cross section, you can actually see a little bit of weakness in the returns right about there. I think that's probably where you have the conversion to the downdraft. But with time, you can see that weakness actually goes away. And I think that's because the damaging winds are ceasing. So just kind of a pretty classic look there. One other really interesting aspect of this case was the dual pole signatures, especially as it approached the Oklahoma City metropolitan area. The hydrometeor distribution was really unique in that you actually had sort of like an elongated ZDR arc, and that's indicative of slab-like lifting along the leading edge of the gravity wave. In the loop, you'll also see that there's a minimum in your ZDR at the surface too. So it's almost like you have this continuous line of hail. And what's also interesting, I don't think I did a close-up of it, but there's also a gradient in your KDP. So you went from a region where you very clearly had severe hail, you had low KDP, low ZDR, to a region where you had high KDP and low ZDR. So probably a lot of water-coated melting hail. So just a really unique hydrometeor distribution. The other aspect of this too is that there was a supercell with this case. Even though it looks like a bow echo, this is actually like a line of storms with an embedded supercell. There was a long-lived mesocyclone on the southern side or southeastern side of this particular gravity wave, which is where most of the severe hail was occurring. It's actually pretty typical that we've seen with a lot of these cases where you get this really interesting supercell structure. It's like an elongated supercell structure with a really long hook echo. And more often than not, the damaging winds occur near that hook echo region. So it's possible that any dynamic lift associated with the supercell is kind of aiding the up-down trajectory process, aiding that downdraft process. So just a really unique hydrometeor distribution. I did reach out to some folks in Norman to see if they had the phased array radar running for this case. It would have been really, really neat to see this evolution of the dual pole variables in like a much higher spatial temporal resolution. Unfortunately, and perhaps unsurprisingly, the radar wasn't running because we weren't really expecting severe thunderstorms, right? But figured I'll go out on a limb and see if they had that data set just in case. And then just in terms of surface observations through this mature phase, just very impressive. I moved across several mesonet stations with those severe gusts, particularly impressive meteogram at Holdenville, where you can see the very obvious pressure jump is still about 10 millibars. But what's really neat is to see just the humps in the wind as well. You kind of see like 3 distinct humps, as well as a measured wind gust of 86 miles an hour. So just kind of a classic signature of damaging winds produced by GWAC. You can see for the most part, temperature is relatively steady and increases. It is interesting that the temperature actually decreased once the storm passed. So that suggests there actually may have been some sort of cold pour process associated with the storm as well. But I'll point out that the damaging winds mostly occurred prior to that temperature drop. So I still think largely driven by a gravity wave in this case, especially since the pressure did not stay elevated past the storm. So when you see this oscillation in the pressure, that's more indicative of a gravity wave. And then finally, once the storm started to decay as it approached Tulsa, or I guess just south of Tulsa, and especially the Arkansas state line, ironically, the radar in Tulsa had a slightly better radar angle, but that's right when the storm started to decay. But you can see in the base velocity that surface divergence couplet really decayed and basically just like evaporated. That's not the right word. It seized, I should say. And sure enough, the reports of wind damage also went away as sort of that wind signature went away. It's not clear to me at all why the cell started to decay there. As far as I could tell, the environment was exactly the same as points upstream. So I don't know if there's like a synoptic gravity wave that started to outrun the convection. I really don't know. I can't explain it, but just kind of interesting to see the evolution as it approached the Arkansas state line. So just to wrap this up for some concluding thoughts here, this is a really unexpected and a high impact gravity wave associated convective event. A really muted signal on cam guidance, a really meager signal and from an environmental perspective, from the perspective of mute cape. But the overall synoptic pattern with a short wave kind of rounding the base of the trough was favorable for mesoscale gravity waves. And even taking a step back, this was a particularly prolific pattern for gravity waves in general. I think this was the second or third night in a row where there was gravity wave associated convection from the southern plain to the southern Mississippi River Valley. I happened to be working midnight shifts through this whole stretch, so like every single night I was watching GWAC. With my shift partner. He was probably getting sick and tired of me talking about it, but just a really prolific pattern for these types of events. And this is sort of like the crown jewel event through the whole event or through the whole pattern across southern Oklahoma. As I mentioned, it's not exactly clear why that leading cell became dominant, why it went on its rampage, and why it weakened where it weakened. But nevertheless, it's still a very interesting case and one that there was at least a somewhat muted signal and cam guidance. So when it comes to forecasting gravity wave associated convection, it remains a pretty immense challenge. So what I can recommend to everyone is just to be familiar and look out for those favorable patterns. April through June is sort of the peak in the gravity wave season. So we're right smack dab in the middle of that season. Even though right now the pattern across the United States is not super favorable with this like upper level low that's blocking the whole pattern. I suspect the pattern will get more active toward the end of the month. It looks like just favorable MJO phase will probably promote like Western US troughing. So after like May 15th or 20th, maybe it'll get more active. So just to be on the lookout for the favorable synoptic pattern. And then also looking at cam guidance and not necessarily taking it at face value, but just looking for signs that there may be gravity wave associated convection. I don't always recommend like messaging it, like certainly not in like graphics, but maybe not even in area forecast discussions, unless there's like a really strong signal that this is going to occur, because I still suspect we're going to have a high false alarm rate. So the last question, there's more rhetorical, like how can we message these low probability but high impact events? I don't have a super great answer, but I think it's just one of those things we can build into our mental PDF of, hey, this is an environment that could support this kind of low probability, high impact event. Is it going to happen? Probably not. But once the radar starts to show the signs, then you can pivot and get into sort of your severe warning mindset there. So that's all I had. I planned for about 30 minutes there, so I'm glad I went for 31 minutes. I am willing to take any questions if anyone has any questions.
Awesome. Thanks so much, Brett. If you do have questions, please feel free to raise your hand, type it in the chat, or just start talking. Go ahead, Ben.
Hey, Brett, really nice talk. This is something that is always difficult to forecast and even just see happening on radar. We had chatted a little bit about this after I think you had talked about this, but we had a gravity wave, some sort of gravity wave based convection, or maybe just convection causing a gravity wave come through St. Louis pretty shortly after this, I think. And I admittedly haven't looked closely at it, but I do know that it produced a pretty good signature, the pressure drop, but there was almost no winds associated with it. Do you have any tips of things that we might be able to look for to kind of delineate between what's just run-of-the-mill elevated convection and then convection that might do something like this?
Brett, I think you're muted. Hey, Brett, can you hear me? I think you're muted.
I am muted. Thank you for that. I'll just restart my answer. I don't have a good answer for you there, Ben. I don't have any really good tips and tricks. I think that's sort of the mystery of gravity wave associated convection. There has been some promising work out of like Pat Markett's group out of Mizzou, and I know Greg Mann out of Detroit's been looking at like downdraft sin, D-sin. It's kind of analogous to decape, but like you sort of continue integrating like in the inversion. And their work shows that like when the ratio of D-sin is D-sin to decape is like near 1 or less than 1, it's favorable for damaging winds produced by elevated convection. It's not super clear to me if that also applies to this type of gravity wave convection. Some of our early work suggests maybe there's a signal there. But the bigger problem is that D-sin is not produced in a forecast capability anywhere. It's not like you can pull up pivotal weather and look at D-sin at all. It's not in AWIPS. So right now, I do not have any tips and tricks for how to discern whether run-of-the-mill elevated convection will start producing damaging winds other than looking at observations and radar data. Maybe if cam guidance shows a signal for producing damaging winds, that's a sign. But other than that, I don't have anything right now.
All right. Well, that's kind of the way it goes. I guess that's an interesting opportunity then. So yes, thank you.
No problem.
Any other questions?
Perfect. Yes. So that is there's a link in the chat there for the decape D-sin domain. I want to say that's real time. I don't know if that's predictive, like if it shows it in the future. But yeah, in real time, it is actually also on the SPC website. If you look at decape, they do annotate D-sin. I think it's at like -25 and -100 joules per kilogram. But again, it's like real time. It's not necessarily predictive.
All right. Well, I am not seeing any other comments or questions. So thanks again, Brett, and thanks everyone for attending today. This will conclude today's Innovation Spotlight. If you do have further questions for Brett, please reach out to him at a later time. Thanks everyone for joining, and we will see you all later.
Thanks, everyone.